Welcome to MathCabin.com. In the previous video, we found the total number of squares tilted and upright in a square. How about when we have a rectangle? When the number of rows is not equal to the number of columns. How do we find the total number of tilted and upright squares in this figure? So we're going to assume that the smallest shapes are all squares. These cells are all squares. So we're not going to work with the entire figure to figure out the answer and to develop a formula. We'd rather going to look at a smaller version of a rectangle. So we're going to look at this green rectangle, which is a smaller size rectangle than the biggest figure here. And that will be enough to derive a formula that will help us find the total number of squares tilted and upright in this largest figure for any type of rectangle of any size. For this green rectangle, we know that there's 4 rows and there are 9 columns, right? So we're going to say that m is equal to 4, the number of rows, and n is equal to 9, the number of columns. So this is the first possible square that we should consider. And how many of these types of square fit in this rectangle? I'm only going to talk about the tilted number of squares in this video because we already derived the number of upright squares. Okay, so I'm just going to consider the tilted squares. The tilted because the sides are neither horizontal nor vertical. This means that the square in question is tilted, not upright. So this size, the quickest way to determine is to use the product rule. So first you're going to see how much room you got going downstairs, and then how much room you go from this outermost, rightmost vertex all the way to the end. So you see that it has 3 spots vertically, 1, 2, 3, right? So we're going to write 3 times, and then how much across do we go? 1, 2, 3, 4, 5, 6, 7, 8, right? So we can have 3 times 8 possible translations for this given size square, tilted square. Now we're going to look at a bigger version. Possible to move it up or down. It's already inscribed in that respect. However, there's movements across, right? So we know that there's only one movement, one position going down because there's no way you can move this. However, there's 1, 2, 3, 4, 5, 6 positions going to the right, right? So we know that we have 6 combinations or translations of this type of square. We can have also this size and shape. And notice here the symmetry will play a role, because you can also have symmetrically, so as you can see, this is the same exact size and shape as that one, but its tilt is different, right? So you can treat it as a symmetrical version with respect to the midline going through the center of this rectangle. You have to count both of them, okay? So in order to do this, you're going to multiply by 2 the number of movements that you're going to have. And now the movements are 2 down, 2 versions down, and then 1, 2, 3, 4, 5, 6, 7. 7 movements across. And again, we multiply by 2 because we have a cousin symmetrical, same size and shape in this case. We can have this type now. So there will be a 1 version going down, but 1, 2, 3, 4, 5, 6 versions going to the right. But don't forget that there's also symmetry once again. So we have to multiply this result that we have by 2. We don't have any more tilted squares that we can fit in this rectangle. And we have basically 4 sizes and shapes that are possible in this rectangle. So notice now that this is exactly the 4 sizes that we've explored, and we don't have any more sizing for any other tilted squares that can fit in this particular green rectangle. So now letting m be equal to 4 and n being equal to 9, we know we can express these numbers as this, okay? So basically, it will help you understand what the tilted sum is going to be. Notice this is, again, only the tilted sum. Notice that there is a pattern, because if we write them down and combine them, we'll see a pattern. There is m-1 and n-1, and only one product like this, right? So we can write m-1, n-1 plus. Now, how many n-2, n-2 are there? 2 only, right? So we're going to write 2. m-2, n-2. How many n-3, n-3? Notice there's 1 here and there's 2 there. So altogether that's 3, right? 3 m-3, n-3. So now if you just let it go all the way, you're going to see that there's a pattern, because m minus 1 and n minus 1 have a 1 times that you don't see, but it's there. 2 times m minus 2, n minus 2. So basically the coefficient in the front coincides with those numbers that we see that are being subtracted. And now we got to be careful that m is less than or equal to m minus 1, okay? Because m minus 1 should be the highest value for the integer k, because otherwise the whole product, the last product, will be 0. And we don't want the product to be 0, otherwise the whole term that should give you a part of the tilted sum would not make sense, right? So m minus 1 is the highest integer value for the k. M should be less than n. Notice that there's a pattern that will help us find the summation rule for this. First of all, how many products of mn are there? Right? It's going to be 1mn, 2mn, 3mn, all the way until kmn. What's the number of that product we're talking about, right? This is the third product, and then the last product will be the kth product. So that means it's m minus 1th product. We can just write mn, this product mn, and we're just going to write 1 plus 2 plus all the way until we get to k. Negative m, negative 4m, because the 2 and 2 there, negative 9m, so we're talking about perfect squares. So we can just subtract m, and we can just write perfect squares, like 1 squared plus 2 squared plus all the way until we get to m minus 1 squared. Now m minus 1, because that's theoretically the k value, right? We can also change that here, and we can just write m minus 1. After that, we have what? We can write the same thing for the n. So we're going to subtract n, because we have the inner product, negative n, negative 4n, negative 9n, etc. So we can write minus n. So we can write the same thing, the perfect square sum, until m minus 1 squared. And finally, we're going to get to the perfect cubes, because notice that we have a 1, then we have a 2 to the 3rd power, and it's positive because of the 3 2's, 3 3's, and everything is positive there. So we're talking about perfect cubes. Okay, so we can just write plus, because everything's positive going to be, so 1 cubed, 2 cubed, all the way until m minus 1 cubed, right? Because the k is written 3 times here, and we know k is m minus 1, right? So it's going to be m minus 1 cubed. And then the rule for having m minus 1, the sum of the first m minus 1 terms, is going to be basically taking the highest term m minus 1, one higher than that, and then divide it by 2. Now, for the perfect squares, for the first m minus 1 squares, the sum of that, the formula, should be what? Should be m minus 1, the highest one higher than that, which is m, and then don't forget the twice highest, and then plus 1, and then all that should be divided by 6. Okay, and then the same thing here. So I'm going to write minus n, so m minus 1. So I'm just going to copy everything here, except the m is changed to the negative n, because everything else is the same. So m, then 2, m minus 1 plus 1, and then all that divided by 6. Okay, and finally, this will be the sum of the first m minus 1 cubes, all right? And that formula, as you should realize, is going to be what? The highest one, m minus 1, times the next highest, which is higher than that, m, then divided by 2. And don't forget that you should square that, okay? That's the formula for the sum of the first m minus 1 cubes. So now let's combine the upright and tilted sum. So we know from the previous video that when the m is less than n, we know that the upright sum, all right, that's from the previous video. And again, when m is less than n. Now here, noting that these are the terms for the tilted sum, we know that the bottom should be 12, the least common denominator. So we should multiply this whole thing by 2 over 2, which is going to alter these as well. So this will be multiplied by 6, this will be multiplied by 2 every term to make it 12 on the bottom. This also multiplied by 2, and this multiplied by 3 in order to make the bottom 12. All right, it's a little bit messy, but the final answer should be, now you're wondering what would be the formula if the number of rows was a bigger number than the number of columns. So basically what happens if m is bigger than n? Well, you don't have to derive a separate formula for that because you can use symmetry. If you rotate this rectangle 90 degrees, the number of columns will be smaller than the number of rows. If you just rotate it, you just switch the rows of m and n. And that is when the number of rows is bigger than the number of columns. If we want to test the number of tilted and upright squares in this gigantic rectangle, we have to be aware of which formula we use. We use exactly this formula and not the one on the bottom. If you try to use the number on the bottom, you will get a wrong answer. The number of rows is 7 and the number of columns is 12. Okay, so if you do this, the sum on the top, 9,072 divided by 12, that gives us exactly 756 squares.